Hi everybody. The purpose of these videos is to have you actually go through the calculations of electric fields of various distributions of charges. I want you to actually write these out on your own in your notes, and then we're going to review a little bit more carefully when we get back to class on Monday. I may not be able to go through every single detail, but I do want to make sure you get provided written solutions because we do need to move on into Gauss's law and electric potential. So first, we have the electric field due to a point charge, and here we're simply going to take the wonderful Coulomb's law, 1 over 4 pi epsilon naught, and then we have our test charge um, little q, which is something that we're just putting out there to maybe feel the force. And then we have the generating charge, capital Q, right here in the middle, manufacturing the field or putting it out there, divided by um, the distance away from the charge squared. And then we put this little r hat here to indicate that the lines of force are radially outward from the charge q. Now, a couple of things. This is the force, and then the way we actually define the field. Now, if you look at the standard engineering physics textbook, they do this wonderful thing where they say, well, take f and divide it by little q and take the limit as little q goes to 0. And that's all well and good. And what I find is that for AP physics students in their second year of physics, um, it's nice to kind of do this little factoring trick right there. And that stuff in pink is actually what the electric field is, practically speaking. It's almost as though we do a little factoring trick, and then much to our surprise, we do some experiments and discover, oh my goodness, this is actually a real thing. There really is such a thing as an invisible electric field permeating all of space whenever I put a charge somewhere. And when we start studying magnetic fields, we'll actually see there's a relationship between changing electric and magnetic fields. And we actually call that EM radiation. So things like light, radio waves, microwaves, etc., like that awful song that Mr. Mobley's so fond of. So this is the equation for the electric field. Let's just label a couple of terms. So first, this constant, or this sort of glob of numbers here, for lack of a better term, the numerical value of that is 9 times 10 to the ninth newtons meter squared over coulomb squared. Okay, just so you know. And this number epsilon naught is, it's called the permittivity of free space. It's actually related to the speed of light. We'll learn that later on, of free space. And I believe, I'm going to double check, I believe the value is 8.85 times 10 to the negative 12th, but I'm just going to verify that. Yes, in MKS units, it ends up being 8.85 times 10 to the negative 12th. Now, the proper units on this are amps squared, seconds to the fourth, over meters cubed times kilograms. I wouldn't worry about the units. I just worry about this number here because it does pop up in problems. Now, we did define the field before, it's invisible lines of force, and we talked about how the direction and density work, so I don't want to go over that now. The purpose of these videos is really just to get you doing the math calculations to get fields for various objects. So this is the field of the point charge, and we're going to revisit the dipole in the next video.